Welcome to our DBSEC 2020 presentation. The topic of this presentation is non-interactive private decision tree evaluation. My name is Anselme Tueno from SAP in Germany, and this is a joint work with Yordan Boev and Florian Kerschbaum. Let's start with a motivation. Assume we have on one side a server with a machine learning model, and on the other side a client with a data that is to be classified using the server model. When the data is being sent from the client to the server, it can be protected against eavesdropping using encryption. However, encryptions on the server side prevents the compute on the data. So the server has to decrypt it first before doing computation on it. Unfortunately, the data of the client could be sensitive, and the computation and the output of the computation as well could be sensitive. On the other hand, the server model could contain intellectual property. Although regulation might require not to reveal the model in public, because invasion attacks can leak information on the training data. So we'll be dealing with secure computation. So we'll be doing a secure computation that protect both the privacy of the client input and the privacy of the server model, and the computation should reveal only the result of the computation and only to the client. In this talk, we will be dealing with decision trees. So the model of the server is a decision tree, and the data of the client is a features or attributes vector. A decision tree consists of decision nodes and leaf nodes. So each decision node contains a tertiary value and an index pointing on the attribute vector. And the leaf nodes contain classification label which are output as a result of the computation. To do the for simplicity, we will assume that the indexes in the decision node are 1 at the root and 2 here and 3 here. To do the classification using a decision tree, we always start at the root. So we compare x1 with y1, assume that x1 is smaller, then we go to the left, and then we compare x2 with y2, assume that x2 is larger, then we go to the right, and we reach this leaf, which is returned as a result of the classification. There exist several protocols for computing decision tree in a privacy-preserving way. Several of these protocols are interactive solutions. Their communication depends on the decision tree, and the client must perform some computation, which leaks information on the tree to the client, for example, the depth or the number of leaves. Moreover, in the case the client is malicious, the protocol must perform an extra work on the client side. There exists a protocol that is non-interactive, but the communication still depends on the decision tree. The client must perform many decryptions, which leaks to the client the number of leaf nodes and requires a considerable amount of computation to the client. So these solutions are practical in the case where there is a very good network and the client has a large enough computing power. In this talk, we present the protocol that allows the client to send encrypted input to the client to the server, and the server evaluates the entire computation by itself and send few ciphertexts back to the client for decryption. To summarize decision tree protocols, we assume a tree with a depth D and M has a number of decision nodes. The first 3 lines here represent the best interactive solutions with number of rounds at least 4, and they use tools such as homomorphic encryption, garbage secret, obvious transfer, or RAM. The communication depends on the size of the decision tree. They perform D or M comparison and leak either D or M. We have the protocol of LU, which is non-interactive, using fully homomorphic encryption of PGV, but the communication still depends on the size of the decision tree. And of course, M is linked, the number of decision or the number of leaves node is linked to the client. In this talk, we present a non-interactive protocol as well, but the communication is constant and there is no leakage. Before presenting our construction, I want to review the building block, which is basically homomorphic encryption. So we need to generate a pair of public and private keys. The encryption of plaintext X will be denoted like this, and we need to be able to decrypt. The encryption should support addition and multiplication, so it should be basically a somewhat or fully homomorphic encryption. If the depth of the secret that we want to evaluate is limited, then we use in our implementation labeled homomorphic encryption as implemented in HLIPT. If not, then we use fully homomorphic encryption in the Taurus TFG, which supports gate-by-gate bootstrapping. The implementation of HLIP support ciphertext packing. So if we have one bit B, we can pack many copies of B in the same ciphertext. We can also pack, for example, the bit representation of an integer X in the same ciphertext like this, filling the remaining slots with zeros. And the ciphertext packing is compatible with addition and multiplication. So it's basically a vector or a vector addition or a vector multiplication. The operation is also compatible with shift left. So if you have this representation, for example, we can shift to the left by I positions, filling the remaining slots with zeros. Now we are ready to describe our construction. The server starts by comparing all values, so the xi and the yi, and this results in comparison bits. Now we use this comparison bits to label the edges in the tree. So here, for example, at the root, if you have 1 on the left, you have 0 on the right. Here you have 0 on the left, you have 1 on the right. Now we multiply the comparison bits along the path, resulting here in a 0, 1, 0, and 0. These bits are now multiplied with the labels resulting in this one, which we can finally aggregate to get the final result C2. And all these operations are compatible with the homomorphic encryption, so we can put all these values in ciphertext and do the computation on it. After that, we will get ciphertext encrypting C2. However, we have few challenges. The size of the homomorphic ciphertext is large. The homomorphic multiplication is costly, as we see in one of the next slides. Our computation here requires mixing binary operations. These are the operation done at the decision node for comparison. And so we mix binary operations and arithmetic operations. The arithmetic operation consists of the evaluation of the path and aggregation at the leaves node. We provide an optimization for evaluating the path. As you can see, paths have common prefixes. So instead of doing the computation many times, we provide an optimizations for doing this computation efficiently. We'll start by ciphertext packing. So as I said before, HLIP allows to pack many plaintext in the same ciphertext. And we can use this, for example, to pack the classification label. So assume the classification label C has the binary representation C mu to C1, then as explained before, we can pack this plaintext in the same ciphertext like this, filling the remaining slots with zeros. And the computations, the computation along the path result in a bit B, which is actually encrypted like this. So the many copies of the same B in the same ciphertext. So now we can see that we can multiply this one and this one, and we will get the representation of the of the classification label if B is equal 1. Otherwise, we'll get a ciphertext encrypting only zeros. We can also use ciphertext packing for attribute values. So, for example, if the client want to classify many input vectors at the same times, we can pack S attribute in the same ciphertext, where S depends on the encryption parameters. Then we can also pack S copies of the same threshold in one ciphertext, and the ciphertext packing allows to evaluate them together, such that after the computations, we have single ciphertext encrypting the final result. Now, how do we multiply along the paths? First, recall that homomorphic operations add noise to the ciphertext. And if the noise becomes too large, then it's no longer possible to decrypt the ciphertext. According to the original paper of the BTV, if we have two ciphertexts with noise at most B, then the additions produces a ciphertext with noise at most 2B, while the multiplication produces a ciphertext with noise at most B to the square. So this means that instead of multiplying on the path like this successively, which will result in a ciphertext with noise b to the 16th for this case, we'll instead do something like this, where we first multiply b1 with b2 and b3 with b4. Then we multiply this result with this one, and then finally we multiply this result with this one, which results in the ciphertext with noise b to the 8. Optimized multiplication explained on the previous slide is not enough because, as you can see, paths have common prefixes. So to multiply along the paths, if you want to evaluate, for example, this path and this one, we can do something like this, multiplying successively and then multiply also this path. But both paths have this as a common prefix. So we provide an optimization that allows to do this computation only one time, while doing the multiplication efficiently, as explained on the previous slide. And this optimization use direct acyclic graph. So the idea is we divide the tree in sections of at least at most 2 levels. So here 2 levels, and here only one. Then we compute dependency list for each node starting at the root. So at the root, for example, we have no dependency list. Then we go to the level to the first level. So we have here one dependency. So we have B1 in this list and B1 in this list. We do the same at this level as well. We have B3 and B3. So in the next step of the algorithm, we compute dependency list between this one and this one, this one, and this one. And because this node is a leaf, we have to add this dependency as well. And finally, we can do it. We can do similar here at the final levels. And this is a pre-computation that depends only on the structure of the tree, and that is done before the online protocol. Now, in the online protocol, we start from the root to the leaves, and at each level we pop one element and multiply it to the current node in the structure. So here, for example, here at the root, the dependency list is empty. At this level, we have B1, so we can multiply this one with this one and this one with this one. At this level, this dependency list is empty, so there's nothing to do. We have here B2, so we can multiply the result here with this one. At this level, we'll start by multiplying B3. So we do this and we do this. And later we'll multiply B2 with B2 and so on. To summarize, the protocol works as follows. So we have on the client side, you have a pair of private and public keys. The public key is revealed to the server. The client encrypts his input, send it to the server, and the server evaluates all the comparison nodes, all the decision nodes performing comparison, and then the decision paths are evaluated by using a multiplication, and finally the server aggregates the results at the leaf node and sends back the encrypted ciphertext to the client for decryption. In the last part of the talk, I will discuss implementation and result. So we implemented this protocol using HLIP, which is level homomorphic encryption, and TFHE, fully homomorphic encryption on the Toros, which uses gate-by-gate bootstrapping. And here are the results. So here is this graph shows the impact of the optimization of the path optimization presented before. So the orange line is the evaluation without the path optimization, and the black line is the evaluation with our path optimization. And the key takeaway of this slide is that the path optimization that we provided reduces the computation cost in half. This slide illustrates how the computation cost is distributed among the subtasks, which are the comparisons at the decision node, at the evaluation on the evaluation on the path, and aggregation at the leaves node. As you can see here, the cost of computing the input dominates the computation cost. Also, here HLIP to evaluate a 3 with depth 10 with input 16 bits using 72 threads, HLIP takes about 1,000 seconds. On this slide, we have the result of the implementation using TFHE for different input bits using different threads. So here we can first see that the multi-threading improved the computation cost. So here, for example, we have the line for the 32 bit inputs, and here the line for 16-bit input, but they're using a less number of threads. But here we have the lines for 64-bit input and 72 threads, and it shows that multi-threading improved the running time of the protocol. So the takeaway from the previous slide was that for evaluating a decision tree with depth 10 and an input bit an input with 16 bits and using 72 threads, the computation took 1,000 seconds. For the same decision tree with depth 10 an input bit 64 using the same number of threads, TFHE takes 70 seconds. However, HLIP can evaluate up to using the key that we use in our evaluation. HLIP can evaluate up to 720 inputs together, which result in 0.72 seconds per input. We also perform evaluation on real-world datasets. Here, N is the number of features or attributes, D is the depth of the tree, and M is the number of decision nodes. We compare our protocol to the work of Tai and Lu. The work of Tai is interactive. The work of Lu is non-interactive. And here you can see that Tai, the work of Tai, the protocol of Tai is faster, even using 64-bit input. But as I said before, this protocol is interactive and they require a very fast network. Here we have the evaluation result of the work of Lu using using the same test bed as ours. And you can see that Lu use for 12-bit input, our protocol, our TFHE implementation is faster than the work of Lu for larger trees, even for larger for a larger input bit of 16. The HLIP implementation is much more slower, but it can evaluate many input, many attribute vectors together, such that the amortized cost per input is smaller. So to conclude on this talk, I presented a private decision tree protocol between a server and a client. The server has a decision tree model, the client has an attribute vector, and the classification result is revealed only to the client. So as I said before, there are interactive solutions and there are non-interactive solutions. The interactive solutions are require interaction between the clients and the server, and these protocols are practical in setting where the network is very fast and the computation and the server has a large enough computation power. The existing non-interactive solutions does all the computation at the server as our protocol, but it returns as many ciphertext back to the client as there are leaves nodes. In our protocol that we presented in this talk, the client encrypts his input and send it to the server. The server does all the computation by itself and sends back a few ciphertext to the client for decryption. Thank you for listening to this presentation. I will be happy to take any questions. Thank you.